Start with the very next problem. So in problem 3, they tell us that we have a new function machine h of x, and the rule for h of x is shown right here. And they say, okay, what happens if we crank this machine backwards? What that is, what happens if the machine is working like a backwards machine? What would have to be sucked into the machine for 4 to come out the very top of the machine? There are a lot of ways to approach this problem. What I like to do is not what I like to do, but what we can do here is based on the example from problem 2, based on the two tables that we found, the original table and the reverse table, I'm going to use a part of what we understood there to help us think about this problem. So before I start thinking about the backwards machine, I'm going to wrap my head around how h of x is working more concretely. So I'm going to go ahead and create a table for h of x, an input-output table. And I'm just going to choose some simple values for the input here. So I'm going to say, okay, if the input is 1, then according to h of x, it'll be 5 times 1 is 5, plus 2 more, that gives me a 7. If the input is 2, then 5 times 2 is 10, and 2 more is 12. If the input is 3, then 5 times 3 is 15, and 2 more is 17. And let's see, I want 4. Okay, so then what I'm going to do is I'm going to go ahead and think. So this is h of x. And now if I want to know how the backwards machine is working, and if I think about what it means to be a backwards machine, then it should be operating in reverse. And what that means is if the input for the machine is 7, for example, what should come out at the top of this machine? Well, if I look at the h of x here, I expect a 1 to pop out the top if this is truly a backwards machine. If 12 gets sucked up into this machine, then I expect a 2 to come out of the very top. And if 17 gets sucked up into this machine, I would expect a 3 to come out from the top. Okay. And then I notice, just by luck, that if I look at the outputs here, if I continue in this table, the next value would, according to this pattern, it should be a 4. So what I'm going to do is I'm going to go ahead and extend my table. And keep in mind, there's a lot of ways you can go about it. What I could have done is I could also try to find a rule in the same way I found a rule for this table, and then use that rule to help me figure out what would be the input that would give me 4 as an out. But this problem doesn't require me to do that, so I'm going to use the fact that I noticed that 4 would be the next value in my table. So I'm going to go ahead and go to my original function h of x, and I'm going to go ahead and input 4 into this function. So if I input 4, so 4 times 5, that would be 20, plus 2 more, that would be 22. And so thinking about how backwards machines work, that means that that if 22 goes into the machine, 4 should come out of the top. Okay, so that answers that question. So if 22 goes in, 4 comes out. Okay, that's A. Okay, and here we're using an idea that relates the inputs and outputs for functions and their inverses, their undo functions. I'll call them undo. Okay, so now let's look at the next problem here. So we have, I believe the name is Keiko. So Keiko wants to build a new function machine that is the undo of h of x. And what must Keiko machine do to 17 to return a value of 3? Okay, and so here they're asking us explicitly, go find this machine. Okay, so 17. How do you turn 17 into 3? Okay, let's see. 17 into 3. If I subtract 14, okay, 17 take away 14. That returns a value of 3. Okay, so what I'm going to try doing is seeing if that makes sense, seeing if the rule is just take away 14. So I'm going to try the next value in my table. So if my input is 22, then I'm going to take away 14 from 22. So that gives me 22 take away 14. That'll give me a 8. Okay, but I can see here in the table it's supposed to return a 4. So 22 is supposed to give me 4, but if my rule is take away 14, it does not. So taking away 14 cannot be what the machine is doing. So I have to try again. So how else can you take 17 and turn it into 3? Well, 17 is a lot bigger than 3, so I'm going to try, I don't know, maybe I can try dividing it in half. So let's see, if I divide 17 in half, so let's see, I'll try dividing in half, so that gives me 17, that should give me, what is that, 8.5? Okay, but still 8.5 is pretty far from 3. I would have to do maybe a subtraction. You know, if I subtract, let's see, we said 8.5, so if I subtract 4.5, so let's see, if I divide 17 in half, that gives me, here, in fact, this might work easier if I go ahead and use a calculator in case this does not work out. And then I have to keep guessing. So 17, take half of it, so that gives me 8.5. And if I subtract 4.5, that returns a value of 4. Okay, not quite, so I'll subtract 5.5. Okay, there we go, so let me try that. And let's see if this is my rule. So to test it, I'm going to try what happens if I go ahead and plug in 22. So 22, I'm going to use the same rule, 22 divided by 2, so that's 11. And then if I subtract 5.5, I expect it to return a value of 4, but you can see here in the calculation it returns a value of 5.5. So that's not going to work. This whole rule won't work. So I'm going to try again. This time I'm going to, let's see, what happens if I subtract 2. Okay, so I'm going to take away 2. And then that'll give me 17 take away 2 is 15. I need it to return to 3, so okay, what if I divide this by 3? Okay, there. Okay, so I'm going to divide that by 5. That returns a 3. So let's see if it works for 22. So if I have 22 and if I take away 2, okay, that gives me 20. If I divide that by 5, that returns a value of 4. There, oh, that works there, and it worked there. Let's see if it works for 12. 12 take away 2, divide by 5. I need to return a value of 2, and it does. That's nice. And 7 take away 2 divided by 5. I need to return a value of 1, and it does. So there it is. That's the rule right here. This is it. So let me put this into words here. The output is the input less 2 and divided by 5. Now, let me take a moment here and be very honest with you that this method of thinking, of guessing and checking different operations until it fits all the ordered pairs in this table is not very efficient, and it can be a frustrating process. It can take a long time. It requires an element of luck. So, you know, if you're working on this problem on your own and you know, don't feel frustrated, this is just a good way to think about what it means to be a backwards machine, but it's not necessarily the most efficient way to answer the question. We'll be talking about methods in a later problem. But for now, let's go ahead and turn this description into an equation. Recall that we said the outputs mean y, the word is equal, input is x, less 2 means subtract, and divide by 5 is, well, that's self-explanatory. So I'm going to say y is the input less 2 divide by 5. So there we go. This is the inverse for h of x. Okay, so there we go. That's problem B. And in problem C, they say an undue function is called an inverse and has this notation. And the way you read it is h inverse of x. Note that -1 is not a negative exponent. Okay, it's a mathematical symbol that indicates that it's an inverse function of h of x. So it says write the equation. So they're saying write the equation that we came up with up here, this one, using this new notation. So we're going to say, instead of y, we're going to replace this using function notation, this notation here specifically. So we're going to say h inverse of x is equal to x take away 2 divided by 5. So what this does is it communicates to whoever's looking at your work that you have found the undue function, the reverse function, the backwards machine for h of x. And recall that h of x above here is 5x take away 2. Okay, now something interesting that some of you, I know a lot of you are very clever people. You probably noticed a relationship for between h of x and h inverse of x. You'll notice here that we have a subtraction by 2. I'm sorry, let me go back to the original. This is a plus here. That we have a subtraction by 2 here in the inverse, and then we have an addition. You're dividing by 5 here, and you're multiplying. So that's kind of a clue. I'm sure several of you have probably started picking up on that. So what we want to do here is use that relationship. And to get us thinking about how this works is we're going to use some analogies here. So one second, let me get in here.